Hi, my name's Jason. Welcome to my heat transfer video assignment. Let's get started. So here's our question. We have a stainless steel ball that is oven heated up to 300 degrees Celsius. It's then placed into cooling gas at 25 degrees Celsius, and then it cools down to about 100 degrees Celsius. And so we're asked to calculate the H, the external convection factor, and also the time it takes for this cooling process. So here's our schematic. We have a sphere. Here's the diameter. Here's the initial temperature. Here's our cooling gas, 25 degrees, 3 meters per second. And here's our final temperature at 100 degrees. So some assumptions we'll make. We're going to neglect radiation. We're going to assume constant thermal properties. We'll assume no heat loss or heat generation. And this is a one-dimensional heat transfer problem. So the properties are given to us in the question. Here they are for the gas. One hint that the question gives us is that they tell us we can neglect the variation in gas viscosity. And then here are also the stainless steel properties. I will note that I think there's a typo here for this alpha value. I believe it's times 10 to the -6. Usually alpha is never this large. Later on in my calculations, I assume this is times 10 to the -6. So calculating the external convection factor, here are our properties again. First, we'll calculate the Reynolds number. Next, we'll calculate the Nusselt number from our correlations table. This equation only depends on the Reynolds number and the Prandtl number, and then the viscosities also. The ratio of viscosity is 1, like we said earlier, so this comes down to 1. Some checks we have to do before using this equation is we have to check to make sure that the Reynolds number is less than 80,000, which it is. The Prandtl number is greater than 0.7, which it is, and that our ratio is equal to or less than 1, which we assumed earlier. So we can plug in our values, and we get a Nusselt number of 193, and then we have this relationship to convert Nusselt number to the H value, our convection value. So here's kind of our answer for the first part of the question. We get 82.1 for our external convection factor. So now, given our external convection factor, we're going to calculate the time it takes for the steel ball to cool down from 300 to 100. So now it becomes a transient heat transfer problem. We're going to check to see if it's a lump system. To do that, we'll calculate the Biot number. Plugging in our values, we get the Biot number to be 0.36. So if you recall, to use a lumped analysis, the Biot number has to be less than 0.1, which is not the case here. So we can't assume lumped. So we'll just do the spatial analysis. We're going to use the one-term approximation. And so for this, we know almost all our values. We know our final temperature, our T initial, our T infinity. We can look up A1 and we can look up lambda1 from our table, which we'll do next. And so the only thing remaining is just kind of this tau value, which has time in it. So just to note, to use this equation, we have to assume that tau is greater than 0.2. We don't know this yet, but we can kind of assume that for now, and then we'll validate it later. So looking over to our table to get lambda1 and A1, we're going to recalculate our Biot number. So doing that over here, we get 1.1. And so, looking at our table again, we can see that it falls between this range, our values. And so interpolating between these two values, we get a lambda1 of this and an A1 of this. And so now we can just plug everything back into this equation. Plugging in all the values we just found, we get tau equal to 0.411. And so this kind of validates our earlier assumption that tau is greater than 0.2. So we're kind of okay with that. So now tau is equal to alpha t over r squared. And so just plugging in those values, we get a time of 4,000 seconds, which is about 69 minutes. And yeah, pretty basic question. And thank you for your time.